Okay, thank you for joining. So let's start officially the workshop, okay? And again, if you have a question, if you join, for those who will join later, we will have the possibility to summarize a little bit some aspect, and using, of course, the chat, everybody will be informed, and we will have the possibility to share some document. So let me start sharing the presentation for introducing the topic of the workshop. Okay, this is I hope you can see it. Okay, perfect. Can you? Okay, perfect. Okay, so welcome again to this workshop. This is the Design for AM SIG workshop. Thank you very much for joining us. I am Serena Graziosi. I'm an associate professor at the Department of Mechanical Engineering of Politecnico di Milano. I'm leading the Design for AM SIG together with Tino Stanković from ATH and Nicholas Meisel from Penn State University. So the three of us, we are chairing this workshop, but let me thank once again our guest speaker, Zenia Dubrovsky from TU Delft, who has also supported us in the organization of this workshop. So let's go quickly to the topic of the workshop. As I said before, we decided that it was time to speak about AM materials and how the innovation, the AM materials are introducing some radical changes in the way we can design product and develop new technical solutions. And why? Because AM technology means for design engineer, for a research and engineering design, having the possibility to deal with completely different technologies in terms of, for example, the principle, which is at the base of the technology, and also of the raw material that they can use. So we have, thanks to this technology, we have now the possibility to use from metal to ceramics to polymers and other type of material, new one that continuously are available in the literature, but also on the market. So the point is that this wide availability of new materials are posing some challenges. The first type of challenges is related to properties, technical properties, because you can have now the same class of material representing different raw state, let me say. So you can have pellet, you can have powder, you can have filament, according to technologies. And even if the class of material is the same, for example, mechanical properties could not be the same, even if you are using, not only because, if you are using different type of AM technologies, but maybe because you are using powder or filament coming from different suppliers, or also because you are using the same type of technologies, but coming from different type of manufacturers. So every time, what you usually have to do when you are not, you don't have the right mechanical properties of the printed stuff, of the as-built stuff, what you usually have to do is to print your tensile sample and perform a characterization. So in this way, you can get at least the mechanical property that you can use for running your simulation or performing your calculation, let me say. So this is one of the challenges. And the second possibility is, of course, the fact that as design engineers, all of us, I think we have been trained about the possibility to select materials when we start a design activity. So it's material selection, materials and design. So these are two famous books. All of us, we know these books, and still this possibility is valid, of course, in the engineering design field and in general in the product development process. But now, thanks to AM technologies and computational strategies, we can not only select among a wide range of materials, but we have the possibility to design architected materials, the so-called digital materials. So we can use computational strategies to tune locally the distribution of the material, the deposition, for example, the material within a design space. And we can create this kind of non-stochastic structures whose functionality can be designed and controlled from an algorithm, of course. And then we have to print, and then we have to explore what is the output of our design activities. And so these terms, architecture materials, digital materials, are becoming very famous, even both in the literature, but also in outside the scientific literature. And what is extremely interesting is that companies have started to be interested in this kind of material. They are starting to use this kind of non-stochastic structure into products, like these famous Adidas shoes. But we have not only the possibility to design these non-stochastic structures, we have also the possibility to combine different types of material thanks to multi-material printing. So we can create functionally graded materials, which means we can move from one material having certain functionality, certain properties, for example, a soft material, to rigid materials, so to another material having different kind of properties of functionalities. And we can do this by designing. That's the very interesting point. So now, so we have to try also during this workshop to answer to this kind of open question. So how this innovation in AM material is influencing and changing somehow the design process? Do we really have the right knowledge and the right tools, computational tools, to help the design engineer or the researcher in engineering design to exploit this potential related to the possibility to design this kind of multi-material or functionally graded material, let me say, and these architectural materials? And how our educational system should be modified or should be changing, upgraded in order to take into account also these further possibilities. So the point is, we want to push the answer, try to push you reflect on this kind of questions, thanks also to a simple, let me say simple because we have only 1 hour, okay, design task, which is the same design task or similar design task that we use in our summer school, okay, on computational design for M on September. So we all thank Martin Schulz for having given us the possibility to use some slide of his presentation. And the design task is, okay, let's think about this bicycle. And of course, we think about these 4 main subsystems. So the seat post, the frame, the fork, front, and the suspension, and the wheel. How architected materials and functionally graded material can somehow improve, innovate this subsystem of a bike. So we will try to divide you into different teams, and we will try to push you to select one of these subsystems of a bike and try to, again, reflect on how we can innovate this kind of subsystem, integrating architected material and multi-material printing. And of course, try to identify what are the knowledge gaps or the gaps related to the tools that can allow us to perform this kind of activity, because these gaps represent also research opportunities for us. Of course, there are already in this field some very interesting examples, but further ideas can be developed during this workshop. And so this is the overall structure of the workshop. Of course, this is a design task, but to help you reflect on this topic, there will be 2 lectures after this introduction, one on microscale multi-material design for AM, the second one on microscale multi-material design for AM. Then there will be the first phase of the design task that will last 20 minutes, okay? And then there will be another lecture on architected materials by Tino Stanković. And then we will have again another session of design activity where, of course, in the first phase of design activity, you will ask to reflect on your subsystem, take into account multi-material possibilities, multi-material printing possibility, while the second phase you will be asked to reflect on how architected material can innovate your system. And then, of course, after these 2 sessions of design, as a design session, there will be a kind of elevator pitch moment during which each team will have the possibility to briefly present in 2 minutes the ideas that they have developed, and then there will be the final open discussion, then the closing session. So we have many things to do in this workshop, and the idea is to close the workshop at 3:15 p.m. So these are the breakout rooms. Of course, the link to this room are already in the chat, and in the next minutes we will provide you the information on which room you are invited to select for performing the design task. And of course, we will provide you with some extra slide. We have no time now to go into many details, but for each subsystem of the bike, you will find some general technical requirements with a suggestion concerning design goals, okay? And then, of course, we will provide you with some example already available in the literature with some indication about, for example, price, weight, and information about the material, so that you can take as inspiration for your design activity. So I think that's all from my side. So this is a very quick overview of the slide that you will receive for supporting your design activity. So thank you very much. I think it was quick enough. Okay, so let's go back and stop the sharing. Okay. So I think it's time to start with the first lectures from Nicolas. So please, Nicolas, the stage is yours.
Sure. Thank you, Serena. I appreciate it. Let me go ahead and figure out which... There we go.
Okay. Yes, okay. It works. Perfect.
Good to hear. So as Serena mentioned, my name is Nick Meisel. I'm an assistant professor of engineering design at Penn State. So today I'm going to give a very, very broad overview of sort of how do we leverage, or what are some opportunities to leverage additive manufacturing's material complexity at sort of the macro scale. And so then this will feed in directly to my colleague Xenia's discussion in the following lecture. So frequently when we encounter the idea of additive manufacturing, right, we typically think about single material structures. When I teach students about 3D printing, additive manufacturing, usually they think about little plastic doodads, right? So these are little pieces that maybe you'll assemble them together into some sort of complex piece, but they're relatively single material structures. And as you get more towards the industry scale, right, you'll start looking at metal structures as well, beyond just the plastics. But we often think about just one material at a time, and then piecing all of those together. But the reality is that very few of the products we use on an everyday basis are comprised of a single material. So I have a couple of examples here, right? You have your smartphone in your pocket, right? So this is not just a single material. You've got metal, you've got glass, you've got electronics to it. You've got just everyday consumer items. So like, coffee mugs, if you're like me, right? You always have to have your coffee mug with you. Usually you're going to have different material properties there to keep the heat in, to give a soft touch surface at parts of it potentially. Your mouse for your computer, again, different material properties in different locations. So this sort of makes a counterpoint to how we traditionally think of additive manufacturing as single materials, right? We want additive to become better for end-use products, but end-use products are not typically single materials. So we have to try to bridge this divide. So typically, when we have complex multi-material parts, these are all manufactured as single materials, and then they have to get assembled later down the road. And so here's an example of just a Canon digital camera from an exploded view, and this isn't even fitting all of the parts onto this slide. So you can see that most of these pieces are single materials, say for some of the electronics, and each one of
Nick, the slide did not change.
The slide did not change.
Yes, the slides are changing.
I'm still with the one with the few products we use on an everyday basis.
Maybe you have to refresh your browser.
Serena, are you seeing the change?
It came. No, it came.
Okay,
Sorry.
okay. No, no problem, George. Thank you.
Okay. So this is one of the big challenges here is that with additive manufacturing, our whole idea is try to simplify our manufacturing process. But if we still have to create all of these parts individually and then assemble them together, well, we're not really saving any time, and we're not reducing any of the potential points of failure within the structure as well. So this is sort of the hope of multi-material additive manufacturing, is that we can get beyond the need to do all of these very complex single material assemblies. So there are 4 general types of complexity associated with additive manufacturing. You have geometric complexity, hierarchical complexity, functional complexity, and material complexity. So we're focusing for this workshop on that aspect of material complexity, which essentially means that we can vary our materials layer by layer and even in some processes point by point. So I have a couple of examples here, some from the consumer space. So you can see the little printed wheel up here, and the translucent skeletal foot as well. We have multiple colors, like on the bike helmets down here. We even have multiple materials happening in the metals domain, like this piece that you see in the middle and the bottom, and even some multi-material electronics with some conductive filament on the bottom right. So this is a very small sort of smattering of the material potential that's available to us in additive manufacturing. So in the commercial space, we have 3 main processes, I'd argue, that are sort of dominating the discussion when it comes to multi-material additive manufacturing. So the first one is material extrusion. So this is like your common desktop 3D printer, right? So for material extrusion, typically the way that this achieves multi-material structures is that you have multiple nozzles that deposit multiple filaments. And so you can load a different filament into each nozzle to be able to print these multi-material parts. So you would essentially print the layer once with nozzle A and then once with nozzle B. And so that ends up with the sort of structures like you see here, where you have very clearly defined material boundaries. You're not getting very small resolution in terms of the multi-material changes here. So it's happening very much on the macro scale. There are some newer printers that are also using multiple filaments fed into a single nozzle, where you can try to adjust the composition a little bit more on the fly. But frankly, those haven't taken off quite as much as the multiple nozzle, multiple filament approach you see here. Material jetting, this is another process that is very, very highly focused on multi-material additive manufacturing. And so we're taking multi-material droplets that are loaded into these inkjet printheads that you see here, and they're jetted out onto the build platform at a resolution of about 42 microns to create very high resolution parts. So on a macro scale, this is beneficial for us because we have a lot of control over the types of composites we're creating. From a micro scale, it's even more impactful, as my colleague Xenia will talk about in the next lecture. And then the third one is directed energy deposition. So this is one of the main commercial processes for trying to multi-material metals. There are some other processes that are attempting to do multi-materials more in the research space, but for commercial purposes, DED is one of the main ones here. And so the way that this works is very similar to material extrusion. It's just that it's doing it with powder instead of with filament. So you have multiple metal powder hoppers that then deposit your materials onto your substrate. So with these processes, right, and each one has sort of different pros and cons when it comes to the materials that it can handle, the resolution of those materials that it can deposit, it really opens up our design space for additively manufactured parts. But one of the biggest challenges that we face as designers is that if we have, say, geometric freedom, right, which is something we're very typically familiar with in additive manufacturing, I can place material anywhere that I want to. How do I combine that sort of freedom with freedom of our material complexity as well? And so, you know, if I have the sort of plain bracket here on the left, maybe from a geometric standpoint, I could apply, say, topology optimization to this to try to get at a complex geometry. But how do I also then account for, say, if I have multiple material phases? So on the right here, you can see that I have two different material phases in addition to the voids that I can add in for topology optimization. So this is a huge challenge, just trying to intuit what these sorts of designs might look like. So I'll give you a couple of examples of how you could potentially incorporate these multi-materials at the macro scale. So at the most basic level, we can use multiple colors. So colors can be used to communicate different design attributes. So I think one of the most clever ways that we can do this with additive manufacturing is in representing something like FEA. So in this, you see in the background, this finite element analysis that's been run on a GE bracket design. And you're actually able to extract the stress states there as a VRML file and overlay them onto a printed part so that you can actually print out the structure with the FEA overlaid on it. So it helps to communicate where those high stress states might be occurring in your part. We can also use elastomeric materials combined with rigid ones to enable soft touch surfaces. So this is another very common use, especially of material jetting, where you might have part of your structure has to be rigid, and then there are other parts that are going to interface with a human, and you might want them to be a little bit more, a little bit softer to the touch. And so I have a couple of examples here. In the background, you can see this is a shoe sole with a couple areas of soft material combined with rigid material. Up in the top right corner here, you see this little printed stapler. Again, it's mostly for show, but it shows that you can have some of the rigid material, which in this case is going to be the white material. And then you have some of the black material where the user is actually interfacing with it. And that black material is going to be more of your elastomeric material. So some other fun things that we can do with multi-materials at the macro scale. One is leveraging for compliant mechanisms. So compliant mechanisms, if you're not familiar with the general concept, is that you're replacing movable joints with deformable ones instead. So we have one continuous monolithic structure here with the smaller points in it where we actually want to be able to achieve motion. And so those small points allow for deformation. Like you can see with this little elephant here, the little deformable joints on it. So this is typically used in single material additive manufacturing. But one of the challenges you can see here is that these joints have to be incredibly small to be able to function most of the time. So this is where multi-material additive manufacturing comes in. So we can actually combine this with topology optimization to be able to create these same sorts of compliant mechanisms. So this is a slightly different design here. What you would do is you would apply a force on the part to the left, and then you would see a displacement on the little part that sticks out on the right there. But with this design, you can see that because I have access to some of this elastomeric material at the parts where I need the most deformation, my structure doesn't have to be as small in the end as I would on something like the elephant that I just showed you. So this is non-trivial to try to be able to calculate this sort of design though. So this is still an area of very much active research. We can further expand this idea to get to the avenue of printed origami structures. So I've got a couple of examples here. These are actually using shape memory alloys even to be able to deform the structure. But the whole idea is that if you have an additive manufacturing process, they are typically fastest in the XY direction and slowest as your part gets taller. So you can imagine if I could print out an entire structure as flat as possible and then fold it up after it comes off of the build platform, that could save me a lot of print time potentially. So here you see sort of a very simple example of a 3D printed airplane where you have the flexible joints combined with the rigid plates to be able to deform to the final structure. So one thing we have to be aware of, though, is when we're designing these sorts of structures, we have to take care when we're designing the interfaces between them. So if you have any familiarity with overmolding, there are different guidelines to drive overmolded designs, where essentially you need to have these sorts of mechanical interlocks between your material phases. Otherwise, you're going to get easy peeling or delamination between the more elastomeric phases and the more rigid phases. So this is something that we still need to make sure we're accounting for in additive manufacturing and designing these sorts of complex interfaces to ensure that we don't get peeling. We can actually get a little bit fancy with this, so we can combine additive manufacturing's hierarchical complexity with material complexity to try to create functionally graded interfaces, even if we can't use micro scale material deposition. So in this particular case, this is done on a simple two nozzle system from material extrusion. So you design a tapering lattice out of one material, and then you take the negative space and assign that to material B. And you can end up creating this very fine compositely graded interface between your two material phases. Now, this is sort of very high level overview of sort of macro scale design opportunities. But once you start getting micro scale design, things get really wild, right? Because now we can really tailor our material properties to do exactly what we want them to do. So I'm going to pause there, and my colleague Xenia will take it from there. But at this point, Serena, I don't know if we want to do questions now, if we want to wait until after Xenia's had a chance to present.
I think we can, if the audience has some quick question, we can try to, have it now. Are there any questions from the audience? One question? Or maybe, okay, maybe we can postpone the question after the Xenia presentation. We will soon make available the slide concerning the design task. I was only waiting for, because I'm seeing that new participants are joining the session, so we will, after the Xenia presentation, we will share the slide related to the design task. So thank you very much, Nicholas. So now we move to Xenia, so please, the stage is yours. Thank you.
Thank you, Serena. Thanks. Thank you, Nicholas. So let me continue. Okay, everything is up and running. All right, so my name is Zenia Dubrovsky, and I'm an assistant professor at the Faculty of Industrial Design Engineering at Delft University of Technology. And I will be talking about the microscale possibilities of multi-material additive manufacturing. So with micro, it means that we are going to look closer at the smaller scale, and also closer at how different 3D printers actually deposit the materials, because that understanding is actually crucial to create and benefit from the microstructures that we can 3D print. So as Nicholas already explained, many products around us are composed of multiple materials. But if we look closely, we see that different materials are assigned to different regions of the product, and that means that the transitions from one material to the other are usually rather sharp with traditional manufacturing. But there are categories of products where it would be very beneficial to have, for example, smooth transitions. For example, you can think of custom shoes, but also other products like custom-made prosthetic sockets, or maybe even helmets, where you do not necessarily want to have a very sharp transition from one material to the other. And in the examples that I will talk about in this short talk, I will mainly focus on the different material properties that we can achieve with microscale multi-material additive manufacturing and different visual properties. But the same principles can also be applied to properties beyond these two, for example, like conductivity or damping or other properties. So yeah, let's start with mechanical properties. Well, first of all, one of the additive manufacturing processes that is very relevant for microscale additive manufacturing is material jetting. And this technology, as already explained, works by depositing small droplets of material. And in the same way as an inkjet printer that prints color can print multiple colors, different combinations of these materials is possible with this technology. However, if we look closely, we see that this process works by depositing droplets of material basically next to each other. So there's not really active mixing of the materials. So instead of mixing materials, there's actually a structure being created. And these droplets are becoming the elements that build up the part. So it means that, if we want to create a gradient from, for example, flexible to rigid, we actually need to define the different pixels or volumetric pixels, voxels we call them, to create a structure that in the end will inform the 3D printer where to deposit which droplet. And if we, for example, focus on the central region where we have, for example, 50% flexible and 50% rigid material, we can understand more closely what our opportunities are by controlling these different pixels. So say we want to have this 50% flexible and 50% rigid material. One very straightforward pattern that we can come up with is, for example, this checkerboard pattern. And this checkerboard pattern can be used to inform the printer where to deposit which droplets, and the printer will deposit these droplets accordingly. Again, there is some mixing on in between the droplets, but there's no active mixing to create the bulk material. So this is one example of achieving 50% distribution of two materials. But the checkerboard pattern is obviously not the only pattern that can result in this 50% distribution. So a simple alternative would be, for example, to have horizontal lines running through of rigid and flexible. And again, this can be sent to the printer. The printer will deposit the droplets and create this structure. So if we try to imagine the material properties of this structure, we can see that, well, we have rigid, almost fiber-like structures running through our material. If we compare that to the previous one, we can already imagine that the properties of these two structures is very different, while they both use the same amount of flexible and rigid material. And there are many other different printing patterns that we could come up with. Then it becomes very interesting to consider how these different patterns can result in different properties that we can apply in products. For example, going back to the example of the custom shoe sole, say that apart from this desired distribution of flexible and rigid to avoid, for example, pressure points, we also have a desired deformation behavior. Say we want the sole to be able to bend in this mode, but to be stiff in other modes. Well, one possible way of still achieving this density distribution of flexible material, but while still obtaining this desired deformation, would be, for example, to create a printing pattern that looks something like this, with horizontal lines again running through, which would limit the deformation behavior to the deformation behavior that we defined at the beginning. Also, it becomes possible by changing the different printing patterns and therefore the microstructure to create materials that are, for example, flexible for torsion and stiff for bending, or the other way around. This is an example of an application that we have been working on, that is to create soft robotic grippers that have really a desired deformation behavior, making them very flexible for bending, but stiffer for torsion. And also, using this voxel-based multi-material additive manufacturing, we've been looking at understanding how the different ratios, the different printing patterns, and the scale of these patterns can influence the fracture toughness of the resulted part. And combinations, some combinations of these variables have been found to really strongly influence the fracture toughness, as can be seen in these two 3D printed samples that are tested. So the material distribution is similar of flexible and rigid. However, the printing pattern is significantly different, having a very large effect on the fracture behavior. So now let's make the switch from mechanical properties to visual properties. And as an example, I will use a project from my colleagues in Delft. So they are all looking at how multi-material 3D printing can be used to achieve desired material appearances, and they apply that on fine art reproductions. And the challenge there is that a painting is composed of multiple layers of different paints and different transparencies. However, we need to come up with a 3D printing pattern that uses just a limited set of inks and different set of materials. And we need to create something that actually, to the human eye, looks similar. And again, here it's essential to really control the 3D printer on the voxel level or on the pixel level to achieve the desired visual appearance. And next to just plain color, of course, the texture is important. And in this case, also the gloss variation is essential to replicate. And so to capture these elements, you need also custom-made scanners that capture the texture, the color, and the gloss variation. And the data from this scanner is used to generate the voxel pattern for the 3D printing process, which is also material jetting. It's a different platform, but still a very similar technology that is used. Yeah, here you see examples of 3D printed paintings whereby color, texture, and gloss variation was captured and replicated using voxel printing. And just to highlight, also to explain that it's not just material jetting where these kind of technologies can be applied, or where micro scale additive manufacturing can be applied. There's also opportunities to do that for example, material extrusion. As Nicholas already explained, there are 3D printers that can create multiple material parts. And again, usually the different regions of materials are assigned to different areas with sharp transitions. However, these printers are very good at, for example, alternating of having one layer printing in one color or one material and the second layer in another. And that also means that, well, we can slightly offset the extruded printing path to have, for example, to have light material be more visible on the outside, and that creates variations in grayscale. While still using just two materials like black and white, you can still achieve variations of colors in between. Yeah, and that brings me to the conclusions. I'll briefly summarize what I think the challenges are and also what the opportunities are of using micro-scale multi-material additive manufacturing. Well, first of all, most commercially available CAD tools that we're using are really limited to boundary representation. So that means that we don't really have a lot of opportunities to define the inner structure of the material. There are some packages coming out, but it's still limited and also not entirely in the workflow of what most designers are used to. Also, there are some challenges with file sizes, because if we need to describe the entire parts with voxels, we soon end up with parts that are gigabytes large just for small parts. Yeah, finally, so not all 3D printers or all 3D printing technologies have the opportunity to work on this level. Yeah, also the number of materials that we can use is for now still limited, but that's also due to change. And finally, the opportunities. Well, yeah, there are, I think, with this level of multi-material additive manufacturing, there's very interesting capabilities that allow us to design, for example, custom products in which not just the geometry, but also the material properties are assigned to different regions, what is needed for each user. And finally, it's quite exciting that we have now the tools to tune the material properties or even design our own specialized materials behaviors. Yeah, for example, like I explained in the soft robotics example. Yeah, these were my slides.
Thank you very much. I think both two lectures provide you with a wide range of possibilities, not only related to multi-material printing, but in terms of design possibilities concerning technical properties, mechanical properties, aesthetics at different scales. So we have many opportunity to intervene somehow in the design of a new solution or a new type of product and to exploit these multi-material printing possibilities. I don't know if the audience has some questions about these two lectures.
I have a question.
Please, George.
So for me, where do we put the limit between this macro scale and the micro scale? I mean, it looks like it is very shifting limit. I don't know whether there are ways to do it. A couple other things. A lot of the capabilities that we have is to be able to do things that are totally non-linear. Most of our tools are really designed for really linear type behavior. And the third question that has absolutely nothing to do with all this, I cannot figure out how to type in a chat message. Thank you.
So thank you very much, George, because there are very interesting topics in your questions. So for the chat, I think our assistant can help you with on the right, you can, under chat and session, you can directly type inside in the bottom part.
Well, I don't have a bottom part. This is what I'm struggling with. I don't know why.
Okay. Probably because you should use Chrome, the Chrome browser. It is the one suggested by the organizers. Okay, my pleasure. So please, Xenia and Nicholas, would you like to answer to these great questions?
Yeah. So thanks for the question, George. So for the non-linear part, I guess I can say that yes, you're absolutely right. This is one of the biggest challenges, or a challenge that we're having. So I can't speak too much to the specifics of how researchers are tackling that. I typically don't work much in the simulation realm, but I do know that. Especially from an optimization standpoint, the nonlinear seems to be a big challenge here. As far as the how do we transition between the macro scale and the micro scale, right? How do we start thinking about those? I think that there are some ways that we can pull from existing composite theory, for example, to be able to do that. So there's the possibility to design at the micro scale. So like Xenia was speaking about, if you have these different deposition patterns for your multi-material digital composites, then you can use those along with, say, traditional laminated composite theory. So essentially doing the modeling of the material as a whole, and then starting to model the material as a structure. So that's one way to sort of work around those two different scales. I don't know if that answered your question or not, but Xenia, feel free to jump in as well.
Yeah, so also I don't know if maybe I misunderstood the question, but there was also like I understood also where do we place the boundary between micro and macro scale?
Yes.
Yeah, I think that's indeed an important question, and I think what for me is more important, apart from the actual, well, we could set a scale, but I think it's more important where the control over the printing process becomes essential. I think that's where, and not just kind of the CAD file, but really not which geometry the printer is creating, but how the printer is building it up, and therefore which structure it's building. That's where, in my opinion, this level of microscale lies.
Can I add something in here?
Yeah, of course.
Thinking about it, maybe, whenever 3D printers print different materials by themselves, maybe we need to think about that at the macro scale. And whenever there are ways to blend the materials and print them as with variability, then maybe this is when we start talking about the micro scale. What do you think?
Would that also apply to single material AM? Because I think there's also like microstructures that are very important to understand during the design process that apply only to single material additive manufacturing.
Yeah, I mean, I was more thinking about multi-material, but yes, maybe.
Maybe when you design for multi-material, sometimes you have to take into account both when, for example, you're thinking about the design of the interface among the two materials, because if we want to increase, for example, the adhesion at the interface, sometimes you can work both with, let me say, interlocking macro scale interlocking effect, as well as with micro scale interlocking effect. So at the two level you can work. So in this case, there is an overlapping of these two parts. And of course, I think it depends also on the kind of functionalities that you want to exploit the most in your solution. Because also to get the micro origami effect, you have also to work at a micro scale, let me say, for getting this kind of effect.
Something, Serena. Also.
Yes, please.
Yeah, I mean, I also, George had a good question. I also wonder, when you optimize and stuff, and you ask yourselves, when do we cross the boundary? And I think between micro, nano, or macro, and I don't know. I mean, there is not yet a single model that captures all of the effects necessary to show the macroscopic properties at this particular time. And when people ask you, can you do fatigue? I mean, I can't, or crack propagation and stuff like this, because those are some micro effects that will happen in, for instance, in the lattice structure that will determine the overall properties of the material. And I put some slides in my presentation just to show what can't be done, maybe, or what's the current state of art and what people are trying to do. But I don't think there is a unified model that would help us to show. I mean, with origami, it's even worse. I mean, that's another story. But for the basic approach to materials, and you say, okay, this is my material, this is my homogeneous property. There are many points there that are totally unanswered at the moment. And somehow it seems that we are coming back to large-scale structural optimization again when we want to inspect all of the micro effects that come out later on. Yeah.
Tino, for the answer. I think, okay, we are running out of the schedule, but it's not a problem, of course. We have time, we will manage this delay. I think we can start with the design task. Okay, so the idea is this. Tino, do you have the list? Okay, thank you very much. Okay. In the meanwhile, there are people working in the background, let me say, of this work. So we try to divide you into two subgroups. Okay, so we can use 2 virtual rooms that you can join. So this is the first one, Tino, the one that you pasted in the chat.
Everyone.
Okay, that's okay.
Without us, that I could, fish out on the chat,
Okay, so maybe we can have.
So is the number of participants, is that including the people presenting?
Yes,
yes.
And the people in the workshop.
So 13, there's 13 people now present.
And helpers.
Including us. 13 people. 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 13 And okay.
Okay. So maybe we could have 2 virtual rooms.
Mhm.
Okay. Okay. Thank you very much, Dario, for sharing the link. So this is the first one. I think we can split this group. So in the first breakout room, can be joined by Sebastian, Sonia, George, and Peter. Okay, while the second breakout room will be for Pascal, Lorenzo, Joachim, and Dorian. And this is the link for downloading the slide for the design task. So you will have 20 minutes, but of course you are not alone because we will join you in the virtual rooms. So don't worry. And the task, the first design task is to reflect on how multi-material printing at different scale can somehow be used for innovating the subsystem that you have selected as a team among the four that we have identified and are available in the slide. So I think we can, for the moment, stop the plenary, and then we can join the breakout room. Is everything clear?
I mean, yes. Yeah. Sorry.
Thank you, Tino. You're so kind. Okay. So
to make sure
maybe Nicolas and Zenia. Nicolas, you can join breakout room 1. Zenia, you can join breakout room 2, and then of course you can switch. And me and Tino, we will do the same. Okay.
Yeah, and maybe also give, like before, I think asking questions to give them some time to go through the documentation that you said. Yeah.
Yes. Maybe we can check if the link for the rooms works.
Yeah. What happens if I open it?
We'll know soon.
Oh,
yeah, it works.
Yes, yeah.
Thank you, Dario. Thank you very much.
So everyone is now assigned and present in the room.
Yeah.
Okay.
So we are.
We've started some folks in the main space here. I'm looking at the session list. So Dorian, Lorenzo, and Joaquin.
Okay, so
we are a bit behind the schedule.
Yes, I know.
Yeah, we started.
Yes, so don't worry.
Yeah.
We will find a way. So Tino, don't worry. Thank you, Dario. Don't worry, take your time. So don't be scared. We will find a way to summarize the final part.
We only have 2 teams, so the elevator pitches won't be quick.
Okay.
Yeah, that's
good, Nicholas. Good point. And thank you very much for the presentation. They were both really interesting as well as usual. Okay.
Hi, I was, thank you. I was trying to join simultaneously in a different tab, different group.
It doesn't work?
Yes, but I don't know, in Firefox, audio gets all mixed up.
But you are getting your video lags now.
Yeah,
it's a big lag.
So I'm not going to do, I don't advise to do this. Okay, I'm now in room 1.
Serena.
Yes,
until they come back, or how?
No, I think now we can join the breakout room.
Then I go to number 2, huh?
Yeah, I will go. Okay, and so the deadline is 2:20 maximum.
Okay, so got it.
Yes, maximum.
Back here beforehand. Okay, cool. I'll go
there.
Which room? Which one did Then you just go into one.
I don't. Maybe yours is one. Xenia was
Nicholas is yours is in, because Xenia is in 2, I think, also.
okay.
We made this very complicated. I'll go to.
Okay. See you later.
Yeah.
Okay.
Now I don't know who is here anymore.
Me too.
People.
Session.
Ah, there is Lorenzo G still here.
No, but Lorenzo is also in the other.
But if you go to people session and then he is still here on the list.
Probably because he did like us.
Could be.
Because
Could be.
I opened a new tab.
Could be.
That's yeah. So I don't know who are those mentioned by Nicholas.
I can't see them because I have 5 people on the list. Yeah, and
Me too. Me too.
yeah.
Okay.
Let's see.
Let's see. Okay.
Not too many people.
No, I don't know what are the numbers in the other workshop.
Let me take a peek.
Okay. See you later.
I came back in here for a moment just because it seemed like they were very nervous just having one of the moderators like hanging out in the room. So I let them get a little bit of momentum and then pop back in.
But now on the list we have some people that should be in the teams, and they are here.
So Joaquin, I just saw joined in with team 1.
Okay.
And Lorenzo's in there. So I don't know why they're showing up in this
Yeah,
session here.
maybe
They may have multiple screens open.
Could be.
I want to say, I bet if you open it in like a new tab,
Then
as opposed to, then you're in 2 places at once. I bet that's what it is.
So just a question, because I'm trying to do this, but opening into, okay, but the problem is when I do like this, opening in a new tabs, for example, I was in breakout room 1 and I was hearing you discussing in the plenary session. So it was a kind of nightmare for me.
okay, so that does not work.
But the only problem is, I don't know if it is something that deals with me, because Dario brought that. Dario, do you know what is the right way to do this? Because if I open multiple tabs, I always have the background. So even if I unmute my microphone, for example.
Hello, Serena.
Hi.
Okay.
Yes.
I'm your. So you can easily open more tabs.
Mm-hmm.
So you can have open this exploiting material, breakout room 1 and breakout room 2.
Yes.
But if you want to mute them, you can use this sound button in the top right corner.
Ah, okay.
So you can just mute them for yourself, not for everyone.
Ah.
Yeah. Okay. Clear.
Okay.
Okay. Clear.
Great.
Thank you very much.
You're welcome.
Yeah.
Bye.
Cheers. Yeah.
Okay, so we'll try to join breakout room 1 and try to.
In a minute. Give them a minute.
Okay.
Cool.
Yeah.
I did other workshop in the meantime.
Yeah, I think some of the teams like to have the moderator, but I think some of them just want to be able to sit and talk through stuff first, without kind of that feeling of being judged. Maybe, I don't know. Even if we're not judging.
So, Tino, do you have some news about the overall number of participants?
So workshop D12, D13, it's 5 and 7 participants, so not much. But the session that is parallel with ours has 13.
Ah, okay.
So that takes some audience away also.
Okay.
And vice versa. Yeah. Okay.
It's okay. It's not a problem. Not a problem. Even I'm seeing there are 136 participants.
Yeah. I didn't click through all because sometimes, I mean, okay, you pop in and pop out and it's fine, but just want to see.
Yes. Cool.
Shall we go to number?
Yeah.
Yeah.
Yeah, I think we should go because the deadline is in 9 minutes.
Where are you?
Then,
are you guys going to go into? So Zenyo's in 2.
In 2.
Or,
yeah.
No, Zenyo was in 1 actually. He went to 1 accidentally.
But if he's still there, then fine.
Okay, I'll go to 2, I guess.
okay, I will join 1, as you can see.
Okay, then I'll also check 1 and see what's going on.
See you later.
Yeah.
Okay, so I think we are all inside the plenary session. So thank you very much for the interesting discussion inside the breakout rooms. So now it's time to have the third lectures on architected materials from Tino Stanković. And you will use this input for the second part of the design task. So Tino, the stage is yours.
Thank you, Serena. Jenny, can you just please confirm, can you see the presentation?
Yes.
Okay,
Yes.
cool.
Yes.
Thank you. So my name is Tino Stanković. I'm senior scientist at Engineering Design Computing Laboratory, and I'll try to talk about the architecture materials in DFAM in 10 minutes. So I'll focus on the research that I do, which is in lattice structures. So talking about lattice structures, then we discuss in a structure that are modeled as a networks of interconnected structural members, and a generation of such structures is fairly simple, providing that we have a unit cell that is then tessellated through the 3D space to create the overall structure. The unit cell, of course, has in comparison to the whole structure, significantly less elements. And now I have just shown two different examples. On the left-hand side is octet truss that's tessellated 2 by 2 by 2, and one gyroid lattice structure example. This is also tessellated 2 by 2 by 2. So when we talk about architectured materials in general, so the idea is a combination of materials, or base materials, that can provide us with novel properties that are otherwise not achievable with common materials. And both geometry and topology are actually dependent on what we get out. And on this slide, I try to share something in this direction. I showed 4 different structures. So the cubic, based on the cubic unit cell, gyroid unit cell, octet truss, and Kelvin unit cell. And next to each of those structures is their Young modulus that's actually shown for 360 degrees globe for each of the unit cells. And what is interesting to see that different geometry and topology yield with completely different distribution of stiffness in different directions. For instance, cubic lattice only responds in the orthogonal or basic direction, whereas Kelvin is almost isotropic. But it's not only about the distribution of properties, how our architectured material can respond. It's also about getting new combination of material properties. And I took this image from one paper about ultralight, ultra-stiff mechanical metamaterials that, and this chart shows the Young modulus over density plot. And what is interesting about this is just to show that we actually, using architecture materials, are trying to combine the properties that normally with conventional materials don't appear at the same time. And if you take, for instance, red squares or hollow squares plot, you can see that there is a certain range of properties of material that is almost stiff as metal, but at the same time is significantly less dense. That means it's much more efficient and it's light, basically. You can also see that some of the materials retain this property stably. So as you increase the density, the performance, mechanical performance does not change. But for instance, in the case of carbon nanotube foams, you can see that as you reduce the density, the quality or the Young modulus drops significantly. So there are also many pitfalls that can appear in designing metamaterials. Of course, the behavior of material is not only linked to the geometry, it's also linked to the topology. And in this simple chart, I showed normal and Young modulus over relative density plot. And what I'm trying to show that different scaling law actually describes the basic mechanical behavior of each of the architecture materials. For instance, if you have, if the scaling factor equals n, then we discussed, then we actually talk about the stretch dominating structures. And if the scaling factor is above, so in this example 2, then we can talk about bending dominated structures. We actually also discuss the failure, mechanical failure in these materials, whether they are dominated. that allows us for further applications. For instance, here I show this movie often, our ETH logo being 4D printed and then actually trained with the shape memory polymers to develop. This is, of course, auxetic structure, which allows us to have a negative Poisson coefficient. It also allows us to achieve significant large displacements, which was necessary for this example. Then what also Nick was talking about, we have different deployable structures, of course, origami as well. And what is possible, it's possible to design, in this case, an A shows, this is not actually origami, it's prismatic structure with two different stable energy states that occur after snap through buckling in the faces, and then actually can create a configuration, and different configuration actually gives different geometry, and then in the end gives different mechanical performance. And in the B, I show an origami, which is another example that we did. This is not a metamaterial or architecture material, just an example. Also with what was discussed before related to that metamaterials can also be, and architecture materials can also be design deployable, so that once they are inserted, they can actually deploy in their required state at the point of application. Of course, we have combinations of properties, and with this, we usually have sized effects, which I'm not going to discuss now in detail. But for hierarchical structures, of course, each of the bars of the structure we can design further. And this example, I would have a gyroid that's bending dominated because the connectivity is less than 6, and then I have each of the bars of that structure would, in this particular example, be stretch dominated, and then I would have a combination of bending, stretching for the overall material. Of course, if you have stretch, then you have a structure that's high strength and high stiffness. So all of these things are possible. Of course, this design by demand of material happens normally with computational tools, and currently we have the inverse homogenization approaches, which can precisely create unit cells and distribution of material for a unit cell of the properties that we seek. Then we can, for instance, have material databases and data-driven approaches that can also deliver same results. Usually data-driven approaches are propelled by the input data created by inverse homogenization. In the end, we have direct optimization that comes again for the cases when the homogenization can be applied. And this brings us to the computational design methodology that are also shown often. So all of these things we have to take into consideration when designing for additive manufacturing. So we have to think about materials and processes, how to characterize them, because this is the source of many problems that we encounter. Also, the sources are efficient simulation models and computational tools. And just to address some problems, I will show 5 next slides to actually point to these problems. So, for example, all of us have been encountered with this problem. For instance, we optimize this this beam here, and then, okay, the beam snaps correctly this particular time, and somewhere half through the bar at the load that we designed for, but without, increasing the area of the bar around the joints. That did not happen because we didn't account for the moments that happened in the joints, and of course, then the load was not adequate. But there are also many other reasons that contributed to this happening. And as I introduced on the 2 slides before, I was talking about characterization. So there is process characterization. So we already know that many different effects have negative effects on the parts that we print. And in this particular slide that was done from one of our colleagues, of course, the alignment of the bar during the printing had a significant effect on the material properties, which yielded in anisotropic mechanical properties with respect to the orientation of each of the bars printed. And we did this, and we captured this in the mathematical model, in which we showed Young modulus for compression, Young modulus for tension, and ultimate compressive strength, ultimate tensile strength with respect to the orientation of each bar in a lattice structure. However, that's not enough. We have other scaling effects which are negative, not only positive, because positive really happen on nano level. For instance, if you print a ceramic part and then you have the ceramic crystal that is unbroken. It's a single crystal, then you can get very nice behavior. But with respect to the macro behavior, we also can have other different effects that come in. For instance, if your printer can print to micron level, then this study actually shows that the effective properties for buckling with respect to the slender ratio S are actually dependent not only on length but on the cross section of the bar. And if you can see on the image on the right hand side, you can see that the diameter of the bar of each member, when it drops beneath 1.4 millimeters, significantly lose the material properties and can buckle easily. So there are many effects that come directly from the imperfections of the printer that directly influence our ideal architecture material that we thought that we are going to use. This also relates to what we had before. There are different simulation models currently because the simulations are not accurate enough. So for instance, we need dedicated FE simulations. Special problems are not available in generic CAD, for instance, like modeling of the behavior around the joints. Then we can use numerical homogenization, which works well if approximated the globalized behavior with periodic boundary conditions. And that does not happen if we have unit cells within the cells that are not of the same size, which normally happens in engineering problems, and we don't have enough of these unit cells. So actually the periodic boundary conditions are not periodic, and we can't actually apply these techniques. And C, we have multi-scale techniques that are required for analysis of complex behavior, such as fracture and fatigue analysis, which are not possible in N and B. And they actually apply different resolutions of different length scales and model the behavior of material using discrete bars. Finally, computational design methods are also affected. For example, formalization of the underlying search space affects the result, of course. Inverse topology optimization works, but it's computationally very expensive and exhibits its solution non-uniqueness and strong starting point sensitivity of the results. If we can't apply numerical homogenization, meaning periodic boundary conditions, then we have irregular domains for which we need to apply different types of optimization that are close to the straightforward structural optimization. And we have data-driven approaches that work well, given enough training data. So in the example here, you can see for this small parameterized topology-based optimization, you can see that the search space at the right top is completely non-convex. So these problems with the computational tools and optimization are very hard to solve. And finally, about scaling laws, uncertainty, and robustness, there have been significant research that actually try to quantify the behavior of the lattice structure with respect to the uncertainty. So if you move the node of the lattice structure in which the elements interconnect, then the whole mechanical properties would change. And if you look on the left-hand side image, you can see that the Kagome lattice in dark continuous line, actually with the rotation and the perturbation of the nodes, significantly loses the mechanical behavior, and not only the magnitude, also it changes the type. It changes from stretch dominated to bending dominated. So there are many aspects that are still unsolved. And on the right-hand side, we would need, the image on the right-hand side actually shows that we need to have something as a robust optimization or almost formulation, robust generation that can actually create structures that would work for our engineering problems. So probably I'm a bit out of time, and this is it for me. If you have any questions, I would be happy to answer.
Thank you, Tino. Don't worry about the time. It's not a problem. Do you have any question? I think that this lecture clearly underlined the issues that still need to be solved concerning, again, the differences, the imperfections. So which means that what you design is not always what you build, especially with lattices. So mechanical properties as well, which kind of mechanical properties we have to take into account, the initial characterization, and of course the computational part, which is still very challenging. That is also related to to the question of George before concerning the linear part of the problem, which is always easier compared to, especially if we are dealing with elastomeric materials.
Definitely we are not yet there, you know. And when you say I have numerical homogenization, I can solve everything, which is not true. If you take a simple shoe sole and say, okay, I will now homogenize. I mean, you can't because you have 55 cells there, you know. So actually what happens there is much more closer to structural optimization than to numerical homogenization, which you know, implies infinite sheet of material that has certain properties, and also the scale is a bit different. So yeah, lots of things to do.
Yeah, so lots of also opportunities for our engineering design communities. So where our society can really also provide its contribution in this field. Are there any other questions? No? Okay, so I have only one last question for Tino, because you presented many results from your research activity. So it means you always design also your tools for performing this kind of design activity. Is it true?
We are designing our own tools and also our own simulations. Okay. Because somehow we figure it out, it would be the best. Okay, the multi-scale optimization, that was not ours. That's from Dennis Kochman. He's our professor in. This is his field. This is what he does. He does discrete large-scale FEM optimizations or simulations for metamaterials. So that's you can see I provided the sources so you can actually see. But even for our research that is on mesoscale, we always do our own stuff. We also try to consolidate, which is not always easy.
Yeah, I can imagine.
So, yeah, we do our stuff.
Thank you. Question, I mean, we're all designing our own tools and things like this. How do we validate them? Because, I mean, you can go and test something on one machine and you get some results, and you go on another machine, you get different results. So how are we going to come up with something that is really design tools that we could teach and we could use eventually in real life?
Yeah, if I may comment, I totally agree. Because when we test, you know, with some printers, I mean, we wrote down when the testing was done with respect to the time after the printing, because the results change.
Yes.
You know? So I think the problem is not only it's on both sides. You know, we have to understand what are we testing. You know, because you say I didn't get the good results. Yeah, but why? Because maybe the material is not stable enough that it can sustain the same properties in 3 days. You know, so you have to constantly update the material from many aspects, also including the people who produce that material, because they change the composition, which is difficult to all keep together. And all of these imperfections, if it slightly moves, if you have a special architecture, then you will get also better results. So I think you have to know both sides. I mean, for the linear, even for the simple examples, it does not happen so often that you get what you designed for. So I don't know how to deal. I mean, now we know much more than before 5 years ago, you know. It's
I think that now the suggestion is to use kind of consolidated strategies, which means, okay, once you receive the material before and you print lattices, you have to first perform a characterization, which takes time, of course, if you really want to get the proper data for your numerical analysis or for comparing your design tools with the experimental result. So in this field, the experimental phase is extremely important.
But it's not only, you know, it's if you take scaling and you have a threshold that's 1,000 times higher than the threshold of the printer in which the properties don't work anymore. You have to be aware of these things, you know, otherwise you don't know what are you doing. And this is polymers, not metals, is another story.
Yes. Yeah, I mean, a good design engineer, when he or she designs, has always to take into account the influence of the manufacturing process. The point is that for conventional manufacturing strategy, there is already a bunch of literature, and we already teach this kind of stuff, even in bachelor courses, of course. While for AM, it's something new, and every day you have new knowledge about this, also because the technologies are improving very quickly. So also machine and technology materials, because the same type of material coming from different suppliers can provide you with different properties. So I think we have to, probably at a certain point, we will reach a kind of plateau also in the development of these technologies in terms of reliability and resolution, and probably things will be easier from certain point of view. But nowadays, when we design, we have to be really careful about the influence of the printing process and of the material.
But also sharing of the methods that we do. But that's for, to provide each other the code so we can test and see. But that's for a longer discussion. We really need a conference.
Yes.
For that in physical presence.
So I think, thank you very much, Tino, and also thank you once again to Xenia and Nicholas for their lectures. I think we can now quickly move to the breakout rooms, 1 and 2. You should, the link, if you missed the link, they are already in the chat. So you can click on it, and then you will have 15 minutes for discussing about how to use architected materials in your subsystem, and to come quickly to some conclusion that you will be invited to present in the online session, the plenary session, that will start at 3. Okay, so 15 minutes for team activity, very quick team activity. So see you later at 3. Thank you, Dario, for sharing again the link. Thank you very much.
Oh, yeah.
Thank you. Okay.
There is less space than in normal setup.
Yes. No, I think everything is going on well. We are a little bit behind the schedule, but it's not a big issue. Let me say,
because people would like to discuss things.
Yeah, that's why when we started organizing, I was thinking to have this kind of final open discussion if we have time, because I think it's the right place to share some thoughts and some ideas, so which is good.
Yeah, yeah, especially with that's maybe the good thing about a limited number of participants, is that a session discussion with all of us is actually feasible.
Yes.
Yeah.
Yes.
But what did you mean, Tino, with limited space, or?
No, we are. When we were in Delft, it was it's less, not stress. You have more time to talk to people because someone can take you on the side and say, "Hey, I would like to talk."
Yeah.
And you can. Now you can't.
Yeah.
So.
I think it's also tough to just make sure that we have everybody's full focus in the breakout rooms, right? I think everybody's kind of doing 6 different things at once, which is not, I understand. I'm sitting here doing the same thing while other folks are doing their talks. So.
Did somebody check how the other
no.
workshops are doing?
I went
to see
how many people are there, and one workshop had 5, the other 7. healthcare workshop had 22 participants, including the organizers, of course. And the additive manufacturing parallel workshop had 13. So they took some audience.
Yeah.
Okay. So the idea is to The idea is to have the final pitch, and then I have some slide about the summer school result. They will be as a very brief overview of some concept, and in particular of some issues that the students have identified. This is a very brief summary.
Yeah, but that's nice. That's nice. Yeah.
Okay. So I hope we will be able to finish at 3:15. Probably there will be a little bit of delay, 3:20 probably instead of 3. Okay. Then I have to run to my class.
When do you present, Serena? When do you present?
Tomorrow.
And when? Who is your session chair?
Sorry, I don't remember. He's from Zagreb.
Ah, okay. The session chair.
Yes.
Okay.
Tomorrow is the Additive Manufacturing 2, I think. Yeah, I have to check.
And so the key, I didn't check the program in detail, but the keynote from Stratasys, when was that?
I think Wednesday.
Wednesday, but I don't know when exactly.
Okay. So, Tino, you are chairing tomorrow.
I'm chairing from 1 to 2.
From 1 to 2. So I will join also your session.
Yeah, and I'm also assigned to be helper to Christy's session because there are not enough helpers in Zagreb anymore. So I'm there also from 2 to 3.
But Christy
is the session chair.
Of my session?
I don't know, maybe. That's fun. Let me see. I don't know. Tomorrow from 2 to 3, she's the session chair. I don't know which chair, which session. I have to check.
Okay.
But the other, you asked Zenia, it's Wednesday. It's from 2:15 to 3, I think.
Okay, well, I should just check the schedule.
Yeah.
Yes. She's sharing enhance a new card. Okay.
Yeah. Let me grab a coffee.
The book of abstract is really nice. I really like it. The aesthetics is really nice. Okay, so we could try to join the breakout room, or
yeah. So I think actually the direction that the team in the breakout room 1 was going was actually already
clear.
Yeah, but also so that wasn't necessarily multi-material, which is fine. But they were actually already working on architecture. So cellular materials.
Okay. It's interesting because that they selected the wheel subsystem because we had no many example in school about the wheel, so it's interesting.
Yeah, and it's a super interesting challenge.
Yeah,
that
yeah.
Like adaptive behavior based on the surface.
It's complex, yes,
Yeah. But I think the good thing it's very it's definitely challenging, but it's a very clear and defined scope. So that's
yes, you're right.
That's good.
Okay.
Okay, I'll quickly grab something to drink and then I can I'll join the session again.
Okay. Don't worry.
Did Nicholas? Oh, he's back.
Yes.
Entered.
Hello. Sorry, I was just taking out. I was popping into the 2 breakout rooms just to see how they were doing. Looks like both. I was just kind of hiding in the background for them, so not to distract. Looks like both teams are actually. They finally hit a groove on this, so hopefully they'll have something fun to show.
Okay. Good. Okay, they have 7 minutes before the deadline. Okay, cool. I think it's extremely interesting topic, this one, and maybe we can try to somehow create some consideration that we have that came up during the summer school and also during this workshop, because as we all see, there are still many things to do, many opportunities, but also many things to do, and the question raised by George are extremely interesting.
Yeah, absolutely.
And I think that once probably architected materials, it's something that is probably not easier, but to understand, but it's more close to the design engineer mentality or perspective somehow, while multi-material is very challenging, I think. Also to think about how to implement multi-material, probably, I mean, both topics are challenging, but
yeah, I mean, it's crazy, because this guy that does this large scale, multi-scale based simulations, and then you say you use robust lattice structure that I shown there, and it has many elements, and you say, yeah, it's good because the fatigue does not, if you have a crack propagation, then the crack will just crack one member and will stop, which makes sense. But there are examples that you showed me also in which you have one member snapping and then the whole lattice explodes. So, which is unfortunate event. Yeah.
I don't know. Probably you are the expert in multi-material. Probably when dealing with the lattices, probably since you speak about structures, so we can try to figure out, even use the creativity, while for multi-material, maybe it's complex to visualize somehow for not expert in the field, the final result. I don't know, what is your opinion on this? Even if it is more challenging for example, for students to think from a multi-material perspective. I don't know, what is your experience when teaching this kind of stuff?
Who do you ask, me or Zenia or?
No, to Zenia and Nico.
Yeah, I think it's so thinking in multi-material as discrete regions. I think that's the step they can quickly make, in my experience.
Okay.
But then it's quite. Then the challenge starts, because then you want to, even when you show examples, really it's making the. And then so the next thing is gradients. That is still within kind of, not traditional thinking, but it's not too far off. But then when you think about, well, there's multiple ways of making that gradient, well, then
that's
then it becomes complex.
Yeah, because you can co-mold to materials, let me say, but so there is also background knowledge for the
Exactly. Yeah. And gradient. So whenever possible, I use examples like from 2D printing.
Okay.
And they're also like, then you can quite clearly show, well, this is like one way of making a gradient, and it looks like, to the human eye, maybe it's the same, but if you zoom in and look at the pixels, it could be created with different patterns.
Okay. Okay, so 3 minutes before the deadline, I don't know if we have to jump inside the breakout rooms, so we can invite them to join the plenary session. Okay, so maybe Nicholas, can you go to breakout room 2 and someone can go in breakout room 1? Okay, thank you. So,
are you going, Tino, or shall I?
Yeah, I'll go. I'm just looking at the other screen, like what's going on? I'll go.
Okay.
Good. I will drink a little bit of water.
Okay, I let them know they needed to come back.
Okay. Peter, thank you for joining the workshop.
Yeah, no.
It was a pleasure to see you. Yeah. Even if in a virtual mode, we will see.
Yeah.
Okay. So let's wait for the other. I think oh yeah, I think all the participants are inside the plenary session. I think so. Lorenzo, Joaquin, yes, they are joining. I have to refresh the list. One moment. Okay, so we need a presenter from breakout room 1 and one presenter from breakout room 2. I mean, it's going to be an informal speech, so don't worry. I know that you have only a few minutes for discussing. So
That was tight.
yes.
But I think I have a nice picture here.
Cool.
We have. Let's see if I can do the sharing.
Okay.
I almost learned this now. Window. I have so many windows. Let's see. You could do it a couple of minutes ago. Why don't find it? Let's share the screen.
Yes.
Home screen. And nothing happens.
No.
Now it was just stupid. Now I hope you see it. You will be. So, can you see it?
Yes.
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 We took the tire idea. I think it was Fadel that had actually a PhD student working on this. So we will hopefully help him or just make the life more worse. So the idea was, I mean, in tires, we focused on the tire, not the wheel. We focused on the tire. So the left is a hard surface. Then you have a very narrow contact point. And then in normal tires today, it's designed with a specific sort of structure. So it's more or less on that part. So it's very narrow. And then on the sides, if you go deeper, like on the right picture here, if you go deeper on that, you will have more surface structures. You have more studs, or what you can say, on the sides. So that's how you design today. But with multi-material printing, etc., we could change so that the friction, so different type of rubber center, so it's much harder rubber on the center, and also a softer rubber on the sides. To also look at the force distribution, because coming from a point contact, like you have if you go on a very hard surface to more distributed, you can get the momentum, and that momentum you could use to change the behavior of a tire, maybe compliant mechanism, maybe to change the geometry of the tire with some of the things we've seen today. So that is sort of when the distribution of the force will get, contact force get wider, you do something in the tire that maybe sort of move studs out or move geometry that gets soft. But you also saw that sometimes hard surface like in tamarack or sandstone has very high friction. But if you have hard surface like granite that is wet and very slippery, so it's also tricky to go for that part. We haven't decided how to do that, because then you will have contact, but you would to change the air in the tire sort of, so it's softer on soft surface. So that was basically our presentation. Let's go back.
Thank you very much, Peter. Are there any questions from the audience or from the lecturers about this idea? So, Peter, do you think, I mean, the idea is interesting and quite challenging. Do you think you have, what kind of tools would you use to develop this kind of ideas?
I think you have to play and to really understand what is happening in the contact of the wheel, but that is probably available in literature already. So probably you know that the exact so what happens inside the contact. And when we know that, we can sort of use, I think we come up with the use of distribution of the momentum because it gets wider. We can use that in some way to sort of, yeah, some kind of mechanism that will get even wider when it starts to get, even change the tire structure. But what tools, I have no clue. I think it's really, you have to play with how can you create the structure that when something happens from the force distribution, it sort of evolves and get another geometry. I mean, there are some ideas. We've seen several ideas today. So of course it's possible to do. It's just to come up with, to implement it and getting a wheel out of it in the.
Okay, cool. Do you think this solution could also reduce the overall weight of the tire, for example?
Clue.
Okay.
I think it's interesting because a wheel today, if you look at modern fat bikes, for example, they have, I mean, the tire is so much heavier than on a race bike, but on the other end,
We lost you, Peter. Your microphone is mute. Okay.
I didn't do anything. So I think that the weight can be changed because that is sort of how it's designed today. And a race wheel, the tire is super light, but on the fat bike today, the tire is quite heavy, but you have changed the way because you don't have to have any suspension on the, so you can win something maybe to get a heavier tire, but to have less weight in the rest of the structure. So I think that is the way to go.
Okay.
Like on a fat bike.
Okay. Okay, thank you, Peter. So now let's move to breakout room 2. Who is the presenter?
So that would be me.
Okay, Lorenzo, yes, please.
Let me just share my screen as well. Assuming. Okay, it's not allowing me to share the one with the image I made. I don't know why, because it was working in the breakout room.
Does it? Do you get a message, or does the share button not respond?
No. Firefox asks you which window you want to share, and it's
No, it works.
No, it works.
Yeah.
I had the same. I couldn't share a window. I could just full screen, and then it worked.
Yeah, exactly. Sharing window does not work well.
It was working in the breakouts. In any case, yeah. So we were working on a fork, and we essentially we decided to stick pretty much to a very classical kind of idea. So to have a main fork and to replace the damping that is often done by springs with a sleeve made out of a flexible polymer. And allow the front forks to kind of slide along a main central rod that would act as a guide to make sure that the motion is only in a vertical direction rather than horizontal, which would happen if we were to make the entire structure in a flexible material. So that was a very that was kind of the approach we had in mind. Because we analyzed other options such as having a hinge to have a front fork hinge and then include a damper, but the argument against it was that by including the hinge you increase the complexity of the entire system. So we ended up with kind of this main idea.
Oh. Okay, no, it's interesting. So the idea is to replace the standard spring in order to improve the comfort in absorbing bumps when riding. So okay, cool. I understand. So are there any questions from the audience?
We actually started in this direction, but we found out it could be quite easy to manufacture a sort of a spring, some kind of material that behaves like a easy part. The hard part was the sort of the damping, because it's so easy to adjust if you have a hydraulic system with valves. But we talked about, I think it was George that came with the idea of having these snap through things. So you have a sort of a mechanism, sort of a compliant mechanism to stable things that in one direction, but it's hard in the other direction, and then it could be damping. But if you have very, very small of them, so you have several of them after each other, so it goes quite quickly first, and then it starts to be harder and harder and harder, and then the feed be slower, the reverse. So it's easy to push in one direction, but harder in the other direction. And in that way, you could bring a sort of kind of a damping system with compliant mechanism ideas.
That's quite interesting, yeah.
Yeah. So maybe okay, to close the session, and we can also have a brief discussion after. I would like to share with you some results that we got from the student who attended the summer school on computational design for AM. Yeah, I would like to share with you some slide. Let me try to share. Okay. Okay. So okay, so now you can see my screen. Yes, actually on September we organized this summer school on computational design for IM. So there were Xenia, me, Nicolas, Tino, and also Yung Wu, who unfortunately is not present today because he was busy with other duties, but of course he is always part of the team, of our team. So during this summer school, we challenged the student with similar, of course, the same design task. The student, the summer school lasted 11 days, so they had time to reflect on lattices, on architected material, multi-material printing, as well as topology optimization. These are some results from the students who were awarded, or developed some interesting ideas. So, for example, this team worked on the seat and seat post, and so as you can see, the idea was to improve the comfort of the seat with this kind of lattice, and of course to have an integrated design of the seat with the seat post, and using of course also topology optimization to try to also reduce the weight of the overall system. And of course, the student had some challenges to address, because of course the seat has a complex shape and also has also an aesthetic role in a bike, not only functional target. And so, for example, when they were able to create this conformal wireframe for the lattices, but when they try to optimize the structures in a simplified way, of course, otherwise going to be numerically too complex to do. They had to deal with some issues concerning the lack of some beams, so it was challenging for them to go to reach a kind of final design. Okay, combining conformal geometries and optimization, because they wanted to have a graded distribution of the material in order to improve also the comfort according to the rider weight and the rider weight distribution during different type of riding moment.
But it was also due to only one load case.
Ah, yes. Okay. Yes. Thank you, Tino. Yes. Thank you for adding. And this is another example related to the frame and also the fork and the front and the overall suspension system. So the idea of this team was to design a children's bike, and so developing the frame plus the fork and the front as an integrated system. So they also try to develop this kind of compliance system to improve, I mean, the comfort of the riding, but also guarantee the control, of course, of the bike from the rider. And so it's an integrated design. Integrated design. But of course, the idea is to go for this integrated solution but they realized that printing this kind of shape using unique technologies is quite complex, and also they realized that developing the frame using topology optimization is interesting and can provide some interesting suggestions to the design engineer, but of course, we have to be always very careful because the risk of having not taken into account further load cases is quite high. And of course, one thing is what you design, one thing is what you build in the end, which means that you have to also to perform not only further simulation, but it's further testing activities, of course, are necessary. And this is another example from Team 3. They went for kind of bias-spire design of the seat and the seat post. Here, the idea was to use a kind of special material that is a kind of liquid crystal polymer that was developed within the research group of one of the lecturers of the summer school. His name is Kunnamasania. And the idea is to use this kind of polymers who has the capability of self-orienting his architecture, okay, it's a microscale architecture in the flow direction. So which means that if we can, and of course improving in this way, guaranteeing a certain level of stiffness following the flow direction, which means that if we can try to print this kind of system using a 5-axis machine, of course you can come out with a complex geometry but with improved mechanical properties. And of course, also the student realized that there are still some challenging, because it's hard to clean topology optimize geometries, because sometimes it provides you with an interesting result, but sometimes with a sparse material distribution. And of course, you perform all the simulation considering the material as isotropic, while it's not always the case, let me say, also because we do not take into account in general, okay, in that case, they wanted to use this 5-axis machine, but otherwise we have to take into account the layer-wise printing strategies. And of course, thinking the fact that they are thinking to use this 5-axis machine increase additionally the level of complexity, because you have also taken into account the way this part is built, which is not standard 2D layer-wise. And this is another example that I added because it's probably has some correlation with the idea of the breakout room 2 teams, let me say. This was quite challenging to design and develop. The idea was to, again, in this case, replace the standard spring with this kind of system, which is characterized by a variable stiffness, which is obtained. So it's a kind of internal module for the fork, for the system to be inserted in the suspension, let me say, and this variable stiffness is obtained through a graded distribution of the material vertically, of course. And the challenging task also for the student was to, okay, I want to design this kind of lattices with a graded distribution material, but first of all, what kind of unit cell I have to select. So this is also a big question also for Team 1, when they decided at the beginning to go for lattices in the seat. Always the same question is, okay, which unit cell I have to select? So this still is an open question, let me say, from a design point of view. And okay, these are some an overview of the result that we got from this summer school, and this last slide. So this was a slide for the closing, is only for remembering you that this Friday there will be a webinar with Mr. Ali Shabi from General Motors, during which we will have the possibility to discuss once again about the role of additive manufacturing technology in the product development process, and how this technology transformed design practice as General Motors. So this is the last slide that I wanted to add, just as a reminder for this webinar, that the Design Practice SIGs has invited us, the Design for M SIG, to co-host. So we are very happy and grateful to the Design Practice SIG for this great collaboration. So I was, I hope, quick enough. So these are some examples from the summer school. There are any questions from the audience about the summer school, or in general about the topics of this workshop? As you can see, there are many possibilities, playing with materials, AM materials, AM technologies. We can once again design new material properties, so architected materials, metamaterial, mechanical metamaterials. There are many keywords in the literature. So I think which means that there are also many opportunities for research.
Yeah, I think it's so many opportunities available today, but it's really hard for common engineer to see this. And this, I mean, it's evolving so quickly. From the presentation we see as Tino, you can actually start to do simulation on these very complex things. It's not, I mean, it's not finished, it's not, but it's starting to do simulations. And when, of course, when we have simulation tools that can manage this, it will be sort of an engineering tool. But the way we can sort of design new things, it's just, it's going to be quite interesting to see how this will develop in years or something like that.
Yes. Now companies, I think, are scared about the use of this kind of, for example, in case of lattices, because still there are many open issues concerning also the presence of imperfections, which for sure affect the final property of the lattices. So that's also risky. There are also issues related to fatigue as well. Even if I can say probably Adidas was one of the first pioneers in this field in introducing lattices inside a commercial product. And probably with the polymers, there are less level of, let me say, complexities on certain point, because it's difficult to make a comparison between metal and polymers. But you are right, new tools are appearing, but still it's difficult to I mean, get into final product.
I think Peter, can I just add something?
Yeah, of course, please.
I think Peter is right. The issue is time that was very short, and explosion of new knowledge that came out, and then how to have an overview that's healthy, you know, that you know that you are informed enough that you can do something that actually makes sense. And it's difficult, and I see this in students, because there's lots of mechanical engineering students that are interested in material science now, you know, because you need concepts from there, you know, otherwise you can't do anything. I mean, you are done, and vice versa. You know, material scientists want to know something about engineering design, because it's also coming to them because they design structures by demand, you know. So it's somehow all came together, and optimization is not even a niche; it's a normal part of the story, you know, without even talking about it. So many fields came together. So it's tough. You know, and our students also ask us after the summer school, I have all of this knowledge, you know, I don't know what to do with it, you know, because it's so much information that comes, they're overwhelmed. So
yeah, and the risk is also that, I mean, the positive point is that we have plenty of information, but since this information also comes from different scientific communities, using different keywords, maybe we are expressing the same concept, but with different keywords or with different terms. And sometimes it's also difficult for the student, or in general, also for us as a researcher, to make a kind of synthesis among different knowledge that is available online, and also, I mean, in the literature. There's also another point. Sometimes also the use of the terms.
Yeah, but we're going from when I was mechanical engineering students in the 90s. I mean, we focused on the spring. We go for mechanical components. It was a spring, force, it was a sort of a distance, and then kind of K value. It was easy to work with. Now we can make a spring that has everything. I mean, whatever idea of a curve, force deformation curve, we can design it. And we can see that, okay, we have a material, okay, we can change the E modulus, we can change the sort of deflection, we can change the structure, we can change the material. It's not a consistent material. It's anisotropic, it's everything. So that's the possibility we have, and that is sort of really hard to because it's so easy to build up with trusses. I mean, we have all done the mechanical engineering of trusses with building a bridge, sort of, and now we have bridges. Yeah, whatever, we can go to micro or macro, and we can build things that is just unbelievable. How to design that? It's just, it's interesting. I mean, to others how to think on this, because it's not like building a bridge with trusses.
No, according to my experience, for example, the best way for the student is to generate concerning the experience concerning lattices. For example, you try to with small and easy sample, let me say, of different type of lattices having different behavior, whether bending or stretching, and then you push them to try to perform experimental tests so they can really see the deformation, any kind of effect occurring in the lattices. This is the first step, okay? Then once everything, I mean, the basic, I mean, is clear enough, let me say, you can try to push them doing something a little bit more complex. But I agree with you, it's challenging. And also related to multi-material, for example, probably, I don't know if in mechanical engineering field, polymers are as famous as metals, while in multi-material printing nowadays, the polymers are running very quick. So maybe that was my case. I had to study a lot, background knowledge on polymers before doing my research also in multi-material printing.
But
because, please, Tino.
I want to say, but also, you know, the tools are not available. You know, you have to have students give something to do, and even for lattice structures, you know, we had a hard time to create this grasshopper rhino thing that worked for summer school, but and it was suboptimal, and I mean, we knew all of these things that are inside, but you can't just, you know, give it to students and say optimize this domain for some that does not exist yet, so it's not so available. There are many constraints and many obstacles, and it's simplified, and it's a lot, and deployable structure. What also Nick showed, you know, origami, that's even worse. Also, I don't know. I mean, the curriculum should change. You know, that's what I can observe. What we do, you know, and it's directed more, and then you have to teach them all of these things. And students are interested, because I also think about when I was studying naval architecture, okay, but it was the same. Material science wasn't so exciting. Sorry, it's recorded, but it wasn't so exciting because you had steel and it ended there, And now it's much more exciting because in architectures you can design stuff. It completely changes the perspective. So,
yeah. Thank you, Tino. I don't know whether Xenia, Nicholas, would you like to add something as some closing comments for the multi-material, for example?
Yeah, but also to add a little bit, I think it's what I notice. It's because this field is also still developing. Teaching about this is also quite different than teaching established or traditional disciplines. Which is also, in a way, I think is exciting because that also means that students and students' work can be part of the development. And so I think that's also one of the points I kind of use to make them enthusiastic, because sometimes indeed they're overwhelmed and they say, well, how do I know what the result will be? Like, well, right now nobody knows, but maybe you can figure out. So that's I think significantly different from teaching like injection molding things or already established things.
Thank you, Xenia. And Nicholas, one last comment.
Yeah, no, I echo Xenia's comments. I think this is, as difficult as like traditional design for additive is right now, and how difficult that is proving to be. I think when you start adding in this extra challenge about, how do we design with multi-materials, right? So now we're adding an extra layer of complexity to it. I think it just takes it to a place where we're just honestly not ready to handle yet as engineering designers. And I think we're going to get there. We're starting to see the tools appear, and we're starting to understand some of the fundamentals of it. But I think that we still have a lot of ways to go. And I think that, as you mentioned, being able to pull in examples as the students are learning it can be really beneficial.
Okay. Yes. Thank you for your comments and for sharing your experience, both as researchers and as educators as well, of course. I don't know if there are any comments from the audience. I think it was kind of
constantly
a long without a break. We know that the organizer suggested to have a break, but was difficult to manage. So I hope. So let us close this session. Of course, we thank you a lot for participating to our workshop. I invite you to stay tuned to Design for EMSIG event. I'm sure you will enjoy the Design 2020 conference. And of course, again, it was a pleasure. Let me thank once again Nicholas, Tino, and Xenia for their lectures, and in particular Xenia for joining the workshop as our guest speaker and co-organizer. Okay, so thank you once again. And of course, if you have a question about these topics, which is extremely interesting for scientific, don't hesitate to contact us and write emails. So we will be pleased to answer. Okay, Tino, I saw your hand.
Yeah, no, I'm just answering because people asked about the slides and stuff, and I gave my email, or any of the organizers, just send us email so we can reply. Peter also send me, and then we can organize the slides in PDFs, and I think it's no problem to share.
Okay, perfect. Yeah, for sure. Cool. So thank you very much once again, and enjoy the conference, the Design 2020 conference. So see you. I hope to see you at the additive manufacturing session. Please remember.
I will be there at least.
Okay, cool, Peter. Okay, bye-bye. Thank you once again.
Thank you. Bye.
Bye.